So yesterday I defined div and curl, and we talked about how you could rewrite the Stokes theorem in classical form. And I wanted to elaborate a little bit on how that gives you physical interpretations of these things. You will have a web work problem opening today after class that draws you a bunch of vector fields in the plane and asks you what their div and curl are, qualitatively, not formulas. So you don't have formulas to compute with. You have to look at things and say, div of this vector field is positive, div of this one is negative, curl, this one is pointing up, curl, this one's pointing down. So I want you to develop some intuition. Yes, Gabe?
You may have already, or you might answer this, but what are the physical interpretations of
That's what I'm doing. So we said that if you took the case of a compact, oriented, two-dimensional manifold with boundary, you got that the integral of f dot t around the boundary, so that's the work done by f going around the boundary, is the flux of curl f across the surface. This should remind you of what happens when f is conservative. What's this side?
0.
And if f is conservative, it is a gradient of somebody. Therefore, curl of a gradient being 0, this side's 0 as well, for any surface. So that checks our previous knowledge, okay? So this was the classical thing that's actually got Stokes' name on it. And then if V, I guess I called it omega yesterday, is a compact region, so I don't need compact because it's a region. It's already compact. If omega is a region in R3, then integrating the f over the boundary of that region, namely finding the flux of f across the boundary, is the integral over the region of div f, which I remind you is a scalar. So how much stuff comes out across the surface is being measured by the divergence inside. So both of these are going to lead me to physical interpretations, which I'm about to give Gabe, but everyone else can pay attention. So this is called classically Gauss's theorem or the divergence theorem. You guys are lucky, you don't have to memorize a whole bunch of different formulas and different names on theorems, you just know how to take diaforms and you use Stokes theorem, and it's one swell foop. But if you're communicating with friends who are physics majors or engineering majors or people who have taken regular calculus, they're going to use this language and you should know what they're talking about. Okay, so using these, let's understand div and curl better. Okay, so imagine that you wanted to know what curl of f was at a point. So I'm still suggesting that you think about f as a velocity field in moving water. And I'm ignoring time. I'm just imagining that I'm at some sort of steady state behavior and that the vector field varies from point to point but not varying with time. And I'm at a point in this.
It's like a hot tub or something that's shooting out water. Consistent like a jacuzzi or something.
Okay. And you're not moving inside, so you're, okay.
He's outside the hot tub.
Okay. So you've got a point, and around that point, water's moving around. And you're interested in knowing, in both cases, what these things mean. So what I was starting to suggest yesterday is that you visualize, for example, vector fields that are looking like, just depending on 2 variables at the moment, not on 3, a vector field that is spinning you around a point. So you imagine, as Cameron said yesterday, an eddy or water circulating around, sort of like having a drain there and water's going down the drain, but that's not quite right. So my vector field is in the plane looking like it's tangent to circles. This is just a model, it's not the universal case, but if you understand this, it'll give you intuition. Okay? So what happens if you pick a circle centered at this point A here? And I'm going to do this in general. Imagine picking a point A, and the vector field's doing something around A, and you're interested in knowing how it's curling. So if, for example, it looked like this, you can see that the work done by F around any circle centered at A is a measurement of how strong the force field is, because it's already tangent to the circles. So in the case of this picture, where F is tangent to the circles, you're going to see that the work around a little circle of radius A, oh, I don't want to use A, let's use R. The work done going around a circle of radius R is just going to be proportional to how long the vector field is, because F is already in the tangent direction. Okay? And so clearly, as I take larger and larger circles, I do more and more work.
So here you're choosing the boundary of S to be a circle.
Right, so, and I haven't yet chosen S, but I'm about to. So what I propose to do is to fill in a circle centered at A that's in some tilted plane. Perhaps this is the tilted plane, perhaps it's not. Fill in a circle here of radius R inside a plane with normal vector n. So I'm imagining myself taking a circle in a plane with normal vector n, and I'm allowed to turn my plane and take circles that are oriented different ways in space. Okay? What does this tell me? For, well, I want an S. Well, there's an obvious S. Fill in the disk in that plane. So let's let S be a disk of radius R in the plane with normal n. Then I'm finding, this is constant on S now, right? Because my S is in a plane with constant normal vector. So I'm finding that component of curl F and integrating it over this disk of radius R, and that's telling me how much F does work going around the circle. Well, suppose I wanted to actually get curl of F at the point A. What do I want to think about doing? So I'm thinking about doing an integral of a function over a disk centered at A. Did you do a homework problem, say the first week of the semester? Say that might have come up in yesterday's homework.
You take the average and, or you do the integral and divide by the area.
Right. Yes. Suppose you took the integral over this disk of radius R that's shrinking down to the point F, and you divide by the length of said disk. Sorry. Area. Erase. The area of said disk. Then you're computing the average value, and what do you do with that average value? You take the limit as r goes to 0, and you get the value of the function at the point, assuming the function in question is continuous. So you used this yesterday in homework as well. So do you remember what homework this was?
It was.
So this was actually problem 7 in section 7.1, which said if you have a function that's continuous at A and integrable on a ball around it as you shrink the ball, integral of the function of the ball divided by volume of the ball approaches f at the point. So I'm going to use that here. I get the n component of curl f at A by taking the flux of curl f across a disk of radius r, dividing by the area, and shrinking r to 0. But by Stokes' theorem, this is the limit, as r goes to 0, of 1 over pi r squared times the integral of f dot t over the circle of radius r. And this, I'm claiming, you can see physically. So what I was suggesting you do yesterday at the end of class was that you make a paddle wheel, which I'm terrible at drawing, but there's one in the book. Imagine taking a paddle wheel which has little paddles at the end attached to a spindle in such a way that as the water, this doesn't look right. That does not look right. How should you do it? You want the water to actually push the paddles. So the paddle should actually be along the axis of the spokes there. So if the water pushes on them, it spins the thing around. And you can imagine, with a nice good ball bearing somewhere so there's no friction, that all the energy from the water spinning around is transferred to making this thing spin. So if you stick this spindle in the direction n, this is going to tell you the work done by the force field as you go around the curve is going to tell you how much speed the thing is spinning with. The longer the force field, the faster it spins, because you do more work pushing the particle around there. So what we're seeing is that you can measure what the n component of curl of f is at this point by taking one of these paddle wheels, aligning its axis in direction n, and seeing how fast the thing spins. And you could figure out, so what direction is curl f pointing in? So this can be seen by this angular velocity of the spinning paddle wheel. Now, think back to day 3 of the course last fall. We did dot product. How do you detect the direction that curl f is pointing? If you're allowed to measure curl f at A dot n for various n's, how do you decide which direction the vector is actually pointing?
It would be 2, 3.
It's in the direction of the n that makes this biggest. Right? Dot product is biggest when the vectors are in the same direction. So you can imagine taking the spinning paddle wheel and turning it, varying the n, and at certain ends it's not going to spin at all. Namely, the ends that are orthogonal to the curl vector. And you imagine tilting it and watching it spin faster, and you tilt it over here. Oh, it's faster there. You find the direction spinning the fastest. That's the axis that curl f is pointing along. So curl f tells you, if you try to test out all possible directions of orienting your paddle wheel, what direction do you orient it to get the fastest spin? And then the fastest spin, the angular velocity it's spinning with, tells you the magnitude of curl F.
So N on the paddle wheel is which direction?
Yeah, good. That's this one.
N is that one.
So if you flipped it upside down, or at the spot where it spins the fastest.
It'll spin the opposite,
Way the fastest, okay.
right?
Which
If
would
you
be
put
right-hand
if you
rule.
put your paddle wheel opposite, you've changed the sign here, and in fact it's spinning the other way.
And would you determine the...
No, that's not right.
Yep.
Relative to the
Right.
axis, right. So when I talk about angular velocity, I mean relative, we're back to this again, we're relative to a viewer high above the n vector looking down and seeing counterclockwise, and if you switch n the other way, it's rotating clockwise, which means you get a minus.
So we follow the same right-hand rule.
Yeah.
Direction spinning.
Yep. And the thing I showed you yesterday is the exercise, but I actually did this at the end of class yesterday. If you take f to be a vector, say, k minus y x 0, then the curl of f is k times the vector 0, 0, 2. So the speed with which the thing turns is measuring the magnitude of the curl. This is the angular velocity that it's spinning with. Right? If you compute this, you'll get exactly 2k for this. Okay. So that's what curl is telling you. Div is actually a little easier. So by the way, I was doing this force field spinning you around the origin. Right, I was drawing these pictures where the origin was my point and where the vector field was 0. What would happen if you stuck your paddle wheel over here?
It would still spin. It would still spin counterclockwise.
It's going to spin the same amount because the vector field has the same curl everywhere. It's just not as intuitively clear because here I was clearly spinning around the origin, but here, why does the thing still end up spinning that way?
Because it's on the right path.
On the outside radially, there's more force.
That's
pointing
it.
that way.
You have more pushing this way than you have pushing the opposite way here because the magnitude is proportional to how far from the origin you are. This same argument shows up in the physicist's proof of Gauss's law, which we're going to get to next when you're doing the flux one. Okay. All right, so analogously, how can I interpret divergence? How can I get div f at a point? Well, I can shrink my omegas down to the point A and apply Stokes' theorem down to this point. So I can think of this as the limit, as r goes to 0, of the integral over a ball of radius r centered at A. This is exactly what that number 7 was back months ago. Of div f dv divided by what? I should learn to leave room. Volume. So let me make room for that. 1 over volume of the ball. There we go. Div f dv.
This over a closed pole?
Yeah.
Would it change if it weren't? Yeah, it would.
Okay, and then by Stokes' theorem, or the divergence theorem, in the classical terminology, this would be 1 over the volume of the ball times the flux across the boundary of the ball. All right, integral of divergence is the flux. So how do I visualize divergence? I compute the flux over volume. Flux over the surface divided by the volume inside, take the limit. And that's telling me what the divergence is. So what am I measuring? I'm measuring how much stuff is coming out from the point A. You're taking balls and their boundary spheres that are smaller and smaller, and you're asking how much stuff is coming out relative to how much stuff is coming in the limit, flux divided by volume. So,
Sorry,
go ahead.
why is it, so flux doesn't consider volume and this other?
Well, the flux depends on the surface area, but you scale by the volume because that's what makes it come out right. Just like here, we did line integral around the curve, but divided by the area inside the curve.
So for that example up there, so like the eddy, here would be 0 just because there's something coming out.
That's right. So here, we say A, so the analogous thing to look at here, we say A is a source if div F at A is positive. What's the opposite of a source? Sink. A is a sink. So those of you who have taken 2700 or who will take 4700 will see some of this same terminology showing up in differential equations. If div F is negative, and there really isn't a word that I'm going to teach you for div F being 0 unless it's 0 everywhere. So I'm not going to give you a word. So what does the source look like? Well, source looks like this. If the vector field is coming radially outward from the point, clearly you're going to have flux that's positive. What does a sink look like? Well, it looks like the opposite.
It could be some.
Yeah, now, so I'm right. So I'm not, this is just sort of, this is the analog of doing the rotating around circles picture.
This is just a sink everywhere.
Well, that's a good question.
No,
Neat.
because if you choose a point outside.
So it's clearly a
looks like
sink.
It looks like it is.
It looks like the flux across here is positive, flux around here is negative. Well, now what happens if I take a point out here and draw the thing?
Because the arrows are getting longer, so
Yeah.
that means you're.
It's the
you're
same
adding
argument as up there.
It's the same argument as up there. You're going to have a net positive flux because there's more out than comes in there.
Is it going to be the same?
Well, it depends. So here it actually depends if we're taking the vector field to be literally radially outward with the magnitude of F equal to the magnitude of X, which is what this has. This is the position vector, so the length is growing linearly with how far you are. Then what's the divergence? It's obviously 3. If you remember the formula, well, you're supposed to partial this respect to x, with partial this respect to y, with partial this respect to z. However, if you took a radial force that was inverse square,
Gravity?
like the opposite of gravity, this is a repelling gravity, because I didn't put a minus. So it's the electric field due to a proton, right? As opposed to the electric field due to an electron. I'm looking at the physics people for help.
Physics person.
What's the standard convention on the electric field? Is it attracting if you're a positive charge? You go in, right? Right? Isn't the electric field only done relative to a positive test charge? So if you have an electron here, it pulls in. If you have a proton here, it pushes out.
Right.
So I had it right. I said it right. You're not much help, Michael.
Sorry.
So what do you guys know from the homework you just did? What's the div of this?
0?
It's 0. This has, so that makes no sense, right? What's going on? At the origin, again, these are 3D pictures, but what does the force look like? Well, it blows up. It's huge.
But you can't have the thing centered the origin or include the origin.
It's not defined at the origin. It's getting huger and huger as I move closer and closer, and it's dying out 1 over r squared as I move out. You can't apply this formula in that case, because to apply Stokes' theorem, the force field has to be C1 everywhere inside your region. So the warning here is this formula doesn't apply here at the origin, because the force field is not defined at the origin and you can't apply Stokes' theorem. But if I took myself a little point A out here and took myself a little sphere,
It'd be zero because there's a lot going in, but also
this
a lot
is where
going out.
Physicists make an argument. They call this a Gaussian surface, and they make an argument that because of the way surface area works and the force being inverse square, that then again the net flux there and then going out here, it's positive coming out this side, but it's negative coming in this side. But there's more area compensating for where it's smaller than there is where it's larger, and so they magically wave their hands and argue geometrically that the flux is zero.
But
Sure,
the
but
proof
physicists, they
is, the proof is in doing the divergence calculation.
Well, that's a rigorous proof.
Is that right?
But you can actually make some argument by looking at little pieces of surface and measuring where, compensating the surface area with the strength of the field.
Is this for only balls or just for like any region?
So in fact, you don't, apply that homework problem, it doesn't have to be a ball. You can take any family of shrinking things where you took a cube, or you could take a parallelepiped or whatever, as long as you take the flux across it divided by its volume and shrink uniformly in a way to zero. Okay.
Is that?
That's the,
Okay. So I do in fact now want to remind you guys of what the physicists call Gauss's law, and we're going to do this for the rest of today and the beginning of Friday. So Jonathan's been waiting for this the whole year. So what did we observe about our interesting two-form, which you've now seen again showing up in yesterday's homework? It's closed, but not exact. But if we integrate it around any sphere centered at the origin, we get 4 pi. So we've argued that. That two-form with our dictionary corresponds to exactly this vector field. This is the radial vector field x, y, z corresponds to the two-form x, y, z here, stuck in the slots. Dividing by magnitude x cubed, that's what this is. So this corresponds to, up to a sign and constants, an inverse square vector field, which we just said corresponds to the electric field due to a point charge at the origin, or it corresponds to gravity. If I put a minus sign there, with a minus sign, it's the gravitational field due to a point mass at the origin. And so, since you guys are more used to gravity, except for the people that have done physics recently, I'm going to phrase stuff in terms of gravity rather than in terms of electrostatics. So, but for the physicsy people in the room,
due to point, or does it say point mass? Point mass is 0?
What do you mean with the negative gravitational field? Meaning
Well, because,
pushing out?
right. I
Okay.
mean, really, if you think of gravity, you should have a minus sign because it's, the point mass is pulling you in.
Okay.
So, what does Stokes' theorem, i.e. Gauss's theorem, divergence theorem, tell you in general now about such vector fields? So again, what I'm saying for the rest of today and beginning of Friday talks only about this particular situation. It's not general. I'm talking specifically about a closed to form that's not exact and has this particular integral 4 pi, and it corresponds specifically to this physical setting. So what is Gauss's law in the sense of physics tell us? It tells us the following. For this f, or omega, if you take any surface that happens to be the boundary of a region, what's the flux of f across the surface? So here's my R3. And I could imagine drawing a region that maybe looked like this, filled in. Or I could imagine drawing a region that maybe is the inside of a torus, filled in. What am I going to get when I integrate over the boundary of those regions? When I integrate the flux of this particular force field, or I integrate omega over this particular omega over the surface.
It's going to be the integral of the divergence on the interior, right? So that would be, did we say 0?
So are the answers the same in both cases?
Well, yeah, because you're taking, it's going to be, just by the theorems, it's going to be the
Yeah, but you
integral of
fell right in the
divergence.
trap.
Oh, it doesn't apply at the origin.
If I took a little sphere centered at the origin, what did we just say it was? 4 pi. So I'm going to make the following claim. It's going to be 0 if the origin is not inside omega. But if the origin is inside the region, you're going to get 4 pi. And I'm actually going to be more specific here and say interior of omega here and interior of omega here. And I'm going to say we don't allow ourselves to consider the case when 0 is on the frontier. This integral doesn't even make sense actually. The integral doesn't converge if the origin is on S. Okay, so I'm not answering the question.
Thinking gravity or electrostatics really work. So when would you ever have the origin inside the
Well, so in particular, all right, so, okay, I'll answer that. But do you see what the proof of this is before I do that? If the origin is not on omega, then you can do what Daniel said and apply the theorem. Div f is 0 everywhere inside this region, or d omega is 0 everywhere inside, and the theorem applies because omega is C1 inside. But if the origin's inside, you have to do exactly what you guys were doing in homework yesterday. You have to excise a little ball and apply the theorem to the stuff that's in between.
I'm going to take a limit.
You don't even have to take a limit. You know for a sphere that the answer is 4 pi. Since d omega is 0 everywhere in the region between the sphere and the outer surface, Stokes' theorem tells you that the integral of omega on the outer surface minus the integral of omega on the inner surface is 0.
Because they have opposite.
Because the orientations are opposite.
So it becomes 4 pi.
So in the latter case, fix epsilon small, but you don't have to do a limit, and consider omega sub epsilon, which is the points in omega such that the magnitude is at least epsilon. So do you understand what I'm doing here? I'm just removing the stuff distance epsilon from the origin. Apply, since d omega is 0 on omega, capital omega epsilon, and omega is C1, I get that the integral over the boundary, which is the integral over the boundary of big omega, minus the integral over the sphere of radius epsilon. Why minus?
Orientation.
Right, the boundary orientation, right, points out here and out there means pointing inward. You wanted to say something? Okay. And this is 0, so it tells you that the integral over boundary omega, which is S, is the same as integrating over the sphere of radius epsilon, which we said was 4 pi.
Do we have the equivalent of the winding number?
This is the analog. So
we
this
can't
is the
have it
3D
wind-
analog of winding number.
It can't go around like.
Well, if you can imagine a surface wrapping around and crossing through itself and wrapping around the origin several times, it's exactly analogous.
But it wouldn't be a manifold if it
It will
goes
definitely not be a manifold, but it's still piecewise
through.
something and you can still make sense of it.
Just like how we took apart those curves.
Yeah, exactly analogous.
But we could write it as a manifold with higher dimensions, right? Did we talk about?
No, but the question that why it's asking specifically, is there an analog that we had for winding numbers of
Yeah.
curves around the origin? You would have to take a non-smooth surface in R3 and ask, does it wind around the origin? It's the analogous question. We're staying in R3. Okay, now, I've forgotten what Ken asked. I said I was going to get to it. Did I get to it? I've forgotten what it was now.
Something about for electrostatics.
When would, yeah, like thinking gravity and electrostatics,
Ah.
what does it mean?
So imagine you have a point charge, or you have the, right, I am going to get to this. All right, so apply this to the, I'm going to stick with gravity, just because more people are used to that, and we've talked about it before. So what does this tell me in the case of the gravitational field? So, application. If m is a point mass at the origin, then the gravitational field becomes, this is Newton now, isn't literally what we were writing down anymore. It becomes, there are these constants that show up. There's Newton's universal gravitational constant, there's the minus sign because gravity's pulling you in, there's the mass of the Earth, which is the point mass, m, and then you have x over magnitude x cubed. This is the gravitational field exerted on a unit mass test mass. Okay, so what does Gauss's law tell me? It tells me that if I take S, any surface oriented outwards with the origin in its interior, so I'm in a closed surface here. So I'm taking a region that contains the origin, and I'm asking, take the boundary of that region and ask, what's the flux of the gravitational field across that surface? The flux of F across S is, well, I put in these constants. It's just going to be minus 4 pi gm. No matter what the shape of that surface is, you're going to get the same flux, just so long as the surface has the origin inside it. The simplest case to visualize it is, again, to take a spherical surface of any radius, and then you know that by just computation. All right, we did this calculation. But you get the 4 pi no matter what the sphere is centered at the origin. Okay, so there's net inward flux. Now, what I want to do is generalize this, and then you're going to see we can get something really interesting out of it. Suppose now, and of course you get, if S doesn't have the origin inside, what's the flux? You get 0 still. Okay, suppose now we have a system of finitely many point masses at positions, let's say mi, at positions ai. So imagine now, instead of a point mass at the origin, that you have a bunch of point masses, and the masses might be different. This one might be 1,000,000 kilograms, this one might be a feather, whatever. So what's the gravitational field do to all of them? Let's say I goes from 1 to capital N.
It acts, well, do you mean exactly, or?
Yes, I mean exactly. And that stopped you from saying something that probably wasn't right. So you've got the ith one at point A sub I that has mass m sub I. If you took a test mass at a point x, it gets pulled towards this mass by proportional to the square of the distance, inversely proportional to the square of that distance, and proportional to the mass. It gets pulled towards this one, it gets pulled towards that one, it gets pulled towards this one, it gets pulled towards that one. What's the net force acting on my test mass?
Just the sum
It's
of.
the sum of the various forces. So the net force is the sum of the forces due to each of the masses. Well, you know what I'm going to ask, don't you? Take any region in R3 and take its boundary. Take a region whose boundary does not go through any of those masses. So, if omega is a region with no AI in its boundary, what is the flux of the net gravitational force across the boundary of omega?
It's going to be.
Okay, let someone else think for a sec.
So you're saying it doesn't matter where omega is?
I didn't say that.
Well, you're,
Yeah, it would have to matter. I mean, whether the origin's included in omega.
Well, we don't have an origin anymore.
Everyone's like, A includes some of those.
Oh.
We have these various point masses at these various positions.
And those
Where
are
omega
acting like
is.
Origin.
So
Well, can you be more specific, Cameron?
oh, you make that.
we have
Jackson, you have a conjecture?
If omega's on the interior of the whole
I times the number.
No, close. Minus 4 pi g. Did I leave off the g? No. 4 pi g. Does mass 1 count?
Depends on whether it's part of omega or included in omega.
Okay. So, which masses do I add up?
mass is not inside of
When did the origin count here?
When it is included.
When it is inside. So we're going to sum over the points that are inside omega. The masses that are inside the region contribute to the flux. The ones that are outside do not contribute. That's what our zero told us. If your mass is outside your region, it doesn't contribute to the flux. The net flux is zero, which is this absolute mystery that Newton was the first to figure out, I believe. So what we're getting here is that the net flux counts how much mass is inside your region, and the masses outside don't contribute. You can guess now, if I generalize this, suppose I don't have point masses anymore. This should remind you what we did back with moments of inertia and centers of mass. Suppose I have a region, let's say W, with mass density delta. And let's just for the moment, let's assume it's continuous, say. So instead of having point masses, I'm thinking of having a region of mass with varying density function. Then I can approximate it, just like we did when we did centers of mass and moments of inertia. I can chop it into pieces, and I can think of approximating it by bunches of point masses at various places, where the mass at each point is basically the mass of that little region there. So what do I get? I say the gravitational field due to this mass distribution is still going to be having the flux minus 4 pi g times whatever part of the mass is inside my test region. So if I took an omega that went like this, and I computed the flux of the gravitational field outwards across the boundary of omega, I would pick up the masses that are inside my mass distribution and inside omega. So the generalization is going to be that the flux across the boundary of omega is going to be minus 4 pi g, and what I'm replacing this with is the total mass of my mass distribution inside omega. Right? What masses of my mass distribution are inside my region omega? And what that turns into, in terms of the density function, is the integral over omega of the density.
Intersecting.
Well, so I'm thinking the density is 0 outside omega, outside of W. So this is starting to look more like the divergence theorem. If we say that we can apply the divergence theorem, the flux of f across the boundary of omega is supposed to be the integral over omega of div f. So this is supposed to be the integral of div f. So what do you think div f should be? It should be minus 4 pi g times delta. Now, for those of you who know the physics, this is akin to saying that the divergence of the electrostatic field, the electric field, is 4 pi times the charge density. So, if you ever saw Maxwell's equations, this is one of Maxwell's equations. And it's completely analogous to what we did here, and it's equivalent to Gauss's law, that the flux of the electric field is 4 pi times the charge inside your surface. Here we have gravity, it's minus 4 pi g times the mass inside our surface.
So the more mass you have at a point, the more gravitational force it exudes.
It creates more divergence. So what I'm going to do on Friday is use this to do what Newton figured out and figure out what the gravitational field is inside the Earth. And then what Jonathan's been waiting for, we're going to dig a tunnel through the Earth, drop Jonathan in, and see what happens. And then we go on after that. The second half of next lecture will be a couple of days of topology. So you get to see